Ever find yourself just, looking at something every day, maybe a cup or your hand, and wondering what it's really made of?
Yeah, like down at the very bottom, what's the fundamental stuff?
Exactly. And that's pretty much the rabbit hole we're jumping into today. We've got this really interesting article. It doesn't just ask what the world's made of.
It sort of challenges how we even ask the question, right?
Right. It delves into ontology, the study of being, and introduces this idea called shape dynamics.
Mm-hmm. So our mission basically is to unpack that. We'll look at the core ideas, things like point particles, Euclidean space.
And really focus on how shape dynamics offers this, well, surprisingly different view on how the universe is put together.
Okay, so the article kicks off with a concept that sounds simple enough at first.
Yeah, picture a universe made of just equal mass point particles. Nothing else. Just floating in regular, familiar Euclidean space.
Seems basic. But the kind of mind-bending part is that, in theory at least, all the complexity we see around us.
Galaxies, life, everything
Hmm.
could potentially emerge from just that simple setup.
It really makes you pause, doesn't it? The idea that everything might just boil down to these incredibly basic, almost featureless bits.
It does.
Yeah.
And it feels like a very natural starting point for thinking about reality.
But the article is careful to point out something important.
Oh, yeah.
This kind of structural explanation, however neat it might be, it doesn't really touch the mystery of consciousness.
Ah, right. That feeling of subjective experience. Why it feels like something to be here.
Exactly. That's a whole other huge question, maybe for another deep dive.
Definitely. So, okay, back to complexity from simplicity. How does the article help us visualize that?
It uses a really useful metaphor, I think. Imagine a huge city, like incredibly detailed,
Yeah.
but it's built entirely out of identical Lego bricks.
Ah, I see. So the brick itself is totally uniform.
But the way you connect them, the arrangements, the structures, that creates all the variety. Buildings, streets, everything.
That's a great image. It really highlights how the relationships between simple parts can create totally new emergent properties.
And that idea about relationships and fundamental parts, it ties nicely into the historical context the article brings up.
Takes us way back, doesn't it?
Yeah, to the ancient Greek atomists, and specifically Lucretius.
Right. Lucretius, in his big poem De Rerum Natura, he talked about primordial seeds.
Hmm. These fundamental bits that he thought were the basis of everything, but crucially, he thought they had different shapes.
So like a fire seed would have a fire shape and a water seed, a water shape, something like that.
That was the basic idea, yeah. He figured the different properties we see come from these underlying shapes of the seeds.
It's interesting that even way back then, there was this intuition connecting fundamental building blocks to the forms we observe.
Absolutely. But as the article illustrates with this snowseed idea, that approach starts to get a bit clunky. Like, do you need a unique fundamental particle shape for every single type of snowflake?
Huh, yeah. Okay, it feels a bit ad hoc, maybe. Like you're just making up a new seed shape for everything you see.
Exactly. It lacks that unifying principle.
Nah.
You want an explanation that covers how snowflakes form from simpler rules, not just assuming a snowflake seed.
Right, like understanding the physics of water molecules and temperature, not inventing a specific seed. And this leads to a really crucial distinction the article makes.
Between shape and size, this is central.
Okay, explain that.
So shape, in the context of this article and shape dynamics, is about the intrinsic relationships. You think about a triangle.
Okay.
The angles inside it, they define its shape completely, doesn't matter if it's tiny or huge. Those internal relationships are its form.
Got it. And size.
Size is extrinsic. You need something outside the triangle, like a ruler, to measure how big its sides are. It's a comparison to an external standard.
And shape dynamics, it prioritizes the shape part,
Yeah.
internal stuff.
Exactly. It puts the focus squarely on those internal relationships. The article uses a really neat analogy here, proprioception.
Proprioception. That's our, internal sense of where our body parts are.
Precisely. You know where your hand is relative to your head without needing to look in a mirror or use a measuring tape. You feel your body's shape internally.
That's a brilliant analogy. We just know our own configuration.
And triangles are the go-to example to make this concrete. You can define any triangle just by its internal angles. The side lengths aren't needed to know its fundamental form.
Okay, I'm following.
Yeah.
Shape is internal angles, internal relationships.
Right.
But what about size then? We experience things getting bigger, the universe expanding.
Yeah.
That feels pretty fundamental too. How does shape dynamics handle that?
Well, this is where it really pushes against our everyday intuition.
I thought.
The article basically asks, does the universe really expand relative to some imaginary ruler sitting outside it all?
I mean, that's how we usually picture it, right? Like a balloon inflating into empty space.
Right, but shape dynamics suggests thinking about expansion differently, as an internal change.
Internal.
Think about the relationships between the fundamental points or particles themselves changing. It's not about moving into more space outside.
So, going back to the balloon analogy,
Yeah.
it's less about the balloon skin stretching into nothingness and more like the dots drawn on the balloon are just getting further apart from each other.
Exactly. The change is the changing relationships between the dots. That is the experience of expansion from within the system.
Wow. Okay.
Let's use the triangle again. Imagine the universe as a vast network of interconnected points forming countless triangles.
Right.
Expansion wouldn't mean the whole network getting bigger in some absolute sense measured from outside. It would mean the internal angles of those triangles are changing.
So a triangle might get sharper or flatter.
Yes. The relationships shift. That internal change in the configuration, the changing angles, is the universe growing or transforming from this perspective.
That takes some effort to wrap your head around. It's a completely different framing.
It is. And that's the core idea of shape dynamics as a framework. It's all about the relationships, the shape, not absolute positions or sizes defined externally.
And it uses something called shape statistics. What's that about?
Shape statistics is basically the mathematical toolbox for doing this. It lets you analyze these configurations of points, these shapes, without needing any external scale or ruler.
So you look at a bunch of particles and figure out their arrangement just by how they relate to each other.
Pretty much. You look at the distances, the separations between all the pairs of particles.
Okay. And the article mentioned something called the root mean square length.
Right, that's one tool. It gives you a sort of average measure of these internal separations within the configuration. It's a way to quantify the overall scale internally.
But the really big ideas seem to be about complexity being scale invariant.
Ah, yes. Scale invariant, that's crucial. It means the measure doesn't change just because you zoom in or out, metaphorically speaking.
How does that work?
Shape dynamics achieves this by focusing on dimensionless quantities, ratios.
Ratios of what?
Ratios of those separations between particles. For instance, the ratio of the distance between particle A and B compared to the distance between particles C and D.
So you lose the units, meters, miles, whatever. They cancel out.
Exactly. By using these ratios, the description of the system becomes completely independent of any arbitrary units we might choose to impose. Meters, feet, light years. Doesn't matter.
And why is that so important?
Well, think about it. If the fundamental laws of physics are truly fundamental, why should they depend on whether humans decided to measure things in inches or centimeters?
Good point. It seems weird that a basic law would change based on our measuring stick.
Right. Shape dynamics suggests the fundamental description shouldn't depend on our choice of scale. Its laws are inherently scale invariant because they're built from these ratios. It's, well, arguably a more elegant and fundamental approach.
So the big takeaway, the core teaching here, is that maybe we've been focusing too much on individual things, their size, their location in absolute space.
When perhaps the truly fundamental aspect is how everything relates to everything else. The overall shape of those relationships.
It's a shift from properties of things to properties of the network of things.
Precisely. And that scale invariance idea ties into the fundamental pattern. The relationships should look the same regardless of the scale you're examining. Why should the basic rules care about millimeters versus megaparsecs?
It's really compelling when you put it like that. And, it's fascinating how the article loops this back to the ancient Greeks.
Yeah, back to Lucretius and the atomists.
It shows this deep, long-running human quest, doesn't it? Trying to figure out the basic nature of reality. The questions persist, even as the tools and concepts get way more sophisticated.
Absolutely. It gives you a sense of this long intellectual lineage. Shape dynamics isn't appearing out of nowhere. It's a modern, mathematically rigorous take on some very old, very deep questions about form and substance.
Okay, so let's try and sum this up. This deep dive into the article really pushes you listening, to rethink some basic assumptions.
Yeah, it encourages a shift away from focusing on measurement against external standards.
And towards appreciating the shape of relationships between the fundamental components of the universe.
Right. And the article leaves us with this really evocative final thought.
The triangle feeling its own form.
Exactly. Just like the triangle is defined by its internal angles, its internal relations.
Right.
Maybe the cosmos itself is fundamentally a self-defined web of these relationships.
Not just objects sitting in space, but the relationships are the space, in a way.
That's one way to think about it, a universe aware of its own form through its internal connections.
Wow, okay. So a final thought for you to chew on. Could the fundamental nature of reality be less about what things are individually?
And much more about how they relate to everything else.
Maybe it's time to try and listen to the shape of relationships in how you understand the world. Something to ponder.
Definitely something to ponder.
Thanks for joining us on this deep dive.